In this lecture, I will introduce directional couplers, abbreviated as DC. Directional couplers are important couplers with 4 ports for distribution networks, and we label 4 ports starting from port 1 clockwise to port 4. So port 1 is always be used for input power, and then we have 3 output, port 2, 3, and 4, and for port 2 and 3, we will always assume that the optical power in port 2 is larger than the output optical power in port 3. If it happens in reality that the optical power in port 3 is larger than port 2, we will just label them differently. But always the largest optical power among the two, port 2 and port 3, that port will be labeled as port 2 and the other one as port 3. For directional coupler, a throughput loss is defined in dBs as -10 times log of the ratio P2 to P1, which indicates the reduction in power from port 1 to port 2. As you can see here, I introduced sign minus. So if P2 is smaller than P1 and this ratio is smaller than 1, that expression 10 times log is less than 0, but sign minus will bring it up. So for throughput loss, the answer normally will be positive, but it will be actually a loss. So P2 will be less than P1. Tap loss, by definition, is a signal reduction from port 1 to port 3 in dB. So it's -10 times log of the ratio P3 to P1. Directionality is defined as a signal reduction from port 1 to port 4, and in dBs it is given by this expression -10 times log P4 to P1. In ideal case, nothing should go back to port 4, and therefore the losses here will be infinite losses. And infinite losses meaning no signal propagates there. Typically, of course, it's not infinitely large, but it is normally larger than 40 dB, meaning that signal attenuation at least 10,000 times. Now, we also define access loss, L sub E, as -10 times logarithm of the sum of optical power P2 plus P3 divided by P1. In the ideal case, when optical power does not disappear, but all 100% goes outside and nothing goes to port 4, all the power should be distributed between port 2 and 3. And therefore, sum of P2 plus P3 will be P1. In this case, this ratio is 1, and excess losses 0 dB. But in reality, some optical signal is lost inside the directional coupler. And typically what we lose is few tenths of a dB. And the last parameter is the splitting ratio. It is the ratio between port P2 and P3. For example, if signal is split 50-50 between port 2 and P3, the splitting ratio will be 1:1. Example. Let us have an ideal directional coupler with a splitting ratio 9:1. We want to find throughput loss and tap loss in this system. The ideal directional coupler means that no excess loss inside, therefore P2 plus P3 equals P1, and the splitting ratio 9:1 means that the ratio of P2 to P3 is 9. Now, from this equation, P1 equals P2 plus P3, we will rewrite it, and P3 we will rewrite in terms of P2 using second equation. So in other words, from this equation we solve it for P3, and plug P3 in the first equation. Okay, so with this we will have P1 equals P2. Instead of P3 we will have P2 divided by 9. Adding those two terms together we will have 10 over 9 times P2. And therefore P2 divided by P1, we need to bring P1 to the right side, and 10 over 9 to the left side, we'll have 9 over 10 or 0.9. Therefore, throughput loss by definition is minus 10 times log P2 divided by P1, which is 0.9. Plugging here 0.9, we will get the answer after simple calculation 0.46 dB. So the throughput loss in this case approximately half a dB. Now, as for tap port, P3 over P1 will be 0.1, right? Because together P2 and P3 add up to P1. Therefore, if P2 is 90%, P3 is 10%, and the ratio P3 to P1 is 0.1. By definition, the tap loss in dB is minus 10 divided by P1, minus 10 log of 0.1, and it is 10 dB. We can do similar calculations for a couple of different directional couplers with a different splitting ratio, and I summarize it here for 3 cases. So we start with the central column splitting ratio 1 to 1, 3 to 1, 9 to 1, meaning that here optical power between port 2 and 3 is split 50-50. In this case, optical power in port 2 3 times larger than the optical power that goes to port 3, and in this case optical power that goes to port 2 is 9 times larger than the optical power that goes to port 3. So we already did this case on the previous slide, and we found that P3 to P1 is 0.1 or 1 over 10, P2 to P3 is 9, and tap loss was 10. So signal attenuation in port 3 is 10 dB, and throughput loss is 0.46. That the signal attenuation in port P2 is about 0.5 dB. Now for another directional coupler with split ratio 3 to 1, P3 over P1 is 1/4, and the tap loss is 6 dB. P2 over P3 will be 3, and the throughput loss is 1.25 dB. And splitting ratio 1 to 1, when signal is split 50-50, we have P3 over P2 is 1/2, and the tap loss is 3, and throughput loss, it's all P2 over P1 will be also 1/2, and throughput loss is also 3 dB. So for this specific case, let me mark it. So for this specific case, we have 1-to-1 ratio, splitting ratio, and losses in both throughput and tap ports 3 dB. And normally we will refer to this directional coupler as simply a 3 dB coupler. So whenever you hear 3 dB coupler, meaning is that it is a 1-to-1 splitting ratio. Another exercise. Let us compute a throughput port loss in terms of a tap port loss for an ideal coupler, where there is no excess loss. So by definition, throughput port loss is minus 10 log P2 to P1, but P2 is P1 minus P3, so we can rewrite it as 10 times log P1 minus P3 divided by P1, and we can rewrite it opening the parentheses inside the logarithm as 1 minus P3 over P1. Now by definition, tap loss is minus 10 times logarithm with the base 10 of P3 over P1. So we solve it for P3 over P1, it will be 10 times minus tap port loss divided by 10. And then, so we plug this P3 over P1 into the previous expression to get the final result. Here, that for an ideal coupler, directional coupler, the throughput port loss is minus 10 times logarithm 1 minus 10 to the power minus the tap port loss divided by 10. That is all for this slide.